Good evening, everyone, and welcome to the 14th episode of the Futures webinar series. My name is Anna Jamila, and I am the coordinator of the series. Tonight's topic is Towards Superhuman Autonomous Vehicles, where we will explore vehicle automation and the incredible capabilities these vehicles demonstrate in terms of safety, efficiency, and comfort. We have the honor of hosting Zlatan Ajanović to present this topic. Zlatan is a senior researcher at Virtual Vehicle Research Center in Graz. His past experiences include Prevent Group Bosnia and Herzegovina and AVL List Austria. He was a Marie Curie Fellow within the I-Team project, and he has recently completed his PhD at TU Graz. Zlatan, welcome, and thank you for being here tonight.
Thank you very much. Thank you, everyone. I'm glad to have this opportunity to present you this topic. Before we start with the presentation, I would like just to get some ground rules with you or to explain you my approach. So first, I will give you a very broad picture on the autonomous vehicle topic, and then we will go deeply into one specific part of the autonomous vehicles, which was my focus of my PhD research. Through this, I want you to get the idea how research works, and then we will take these results and really test it on a real vehicle. Through this way, you will see some formulas or some algorithms. I would ask you to not get upset or not get afraid. So there are also some complementary figures, and I presented some of these parts to some high school students, so I'm sure you will manage your way and keep you motivated to the end. My core message is to try to understand intuition in all of the aspects, and then if you have any doubts later, we can discuss on the questions. Just to mention that the work presented here is work done in cooperation with many lovely colleagues which I have, so many of them from Virtual Vehicle Research Center in Austria, many from I-Team project, and also some collaborations which I had during my research stays at University of Sarajevo with Professor Bakir Lačević, and TU Delft with Professor Boris Shirokau, and also Volvo cars like Matic Klomp and Tushar Chu. So I would then start with my presentation. So my presentation is formed as the first part will be introduction. So I will just give you a wide introduction about autonomous vehicles, about the general industry, and also the problems and mainstream approaches here. Then we will focus on the problem which I tackled through my PhD work. From this problem, we will go to three use cases, so which are energy efficient driving, automated driving, and also performance driving. All of these are somehow special use cases of autonomous vehicles. As I said in the title, so Towards Superhuman Autonomous Vehicle, the goal is to achieve superhuman autonomous vehicle. And these three use cases serves us as a backbone or as the main pillars how to achieve this big goal. For all of the use cases, I will shortly give you more or less what is related work in this field, what other people are doing, and then provide you some motion planning solution which we developed, and then show you some results. Eventually, we will come to the conclusion and outlook of this research. So autonomous vehicles actually are not totally new. So we may heard about this recently, but actually for many years people dream to have autonomous vehicles and to have a mobility fully automated, that you come into the vehicle drives you to your destination, and then you exit it and vehicle leaves. One of the first known mentioning was actually Futurama show. So this was organized, this was a big fair in 1939, and it was organized by General Motors. From this point, 80 years now, we come actually to the real vehicles which are being tested and really trying. Many OEMs, actually you cannot find car manufacturer which doesn't have some work on the autonomous vehicles. So what actually means vehicle automation, and what do we come to this? So on one side we have a human driver which traditionally drives the vehicle, and this was always the case. But on the other side we have machine. So now we have this transfer of responsibility of the driving task from a human to machine. So Society of Automotive Engineers actually provided different levels of vehicle automation to kind of to manage this big talk and this big conversation and research work about autonomous vehicles, to steer it and to give some concrete description. So many people interpret this word differently. So we have a level 0 of automation. So this is regular vehicle without any kind of assistance to a driver. So driver is fully responsible for driving longitudinally and laterally vehicles. So meaning taking the steering wheel, controlling the vehicle, and also accelerator, pedal, and brake to have longitudinal driving. And also a driver is overseeing what's happening and adapting to the dynamic situation. Then we have a level 1 of automation. So this means that driving is assisted. In this case, you see, for example, that a driver can lift his feet off. So the vehicle itself controls velocity, longitudinally controls vehicle. Or also it can be that driver keeps longitudinal, but vehicle controls lateral, for example. And we already have many vehicles on our market for many years, almost 30 years now. Vehicles are equipped with, for example, cruise control, where on highway you can turn on the cruise control and then it keeps constant velocity of a vehicle. The next level is level 2. In this case, the driver, this is a partially automated vehicle, and in this case, driver doesn't have to fully control neither steering or the longitudinal, so brake and acceleration. So, but the responsibility is still on the driver. So driver has to oversee what is happening around, and also always take over the control if anything happens. Similar situation with respect to the operation. So the car itself controls longitudinally and laterally vehicle, but the driver can lift off for some time because more or less look on or be disturbed by some other thing, because vehicle itself is responsible for the driving, and vehicle is responsible to notify driver to take over the control. And there is a big step actually going in a validation of a vehicle, and also in implementation, how to come really from a level 2 to level 3. The examples of level 2 are, for example, Tesla. So Tesla for a long time provides level 2, but it always informs driver that it's not responsible for driving. So still driver is responsible, and driver has to take over the control whenever it's necessary. By now on the market, we still don't have any level 3 automated vehicle. Level 4 is the next level. This means that driver can be fully away for some operational domain of a vehicle. So for example, the full highway driving vehicle can do by itself, and driver can fully relax on this. There is one more level, is actually level 5, so-called driver off, because this also means that the vehicle can operate in all conditions where human driver can. So we also don't need a driver, because vehicle can do everything by itself. So the question comes actually, which expectations do we have from autonomous vehicles, and the motivation, why do we need autonomous vehicles? One thing is increased safety. So we have so-called Vision Zero, increased safety in traffic. more than 90% of all accidents actually are caused by human driving failure. And actually, 70% of total fatal accidents in Germany are due to driving failures. The second one is increased traffic efficiency. So if we have autonomous vehicle, we can also optimize traffic flow. So we can also better use free space because vehicle can react faster. We can have vehicles drive in platoons, so on a closer distance together, or they are better informed and so on. So they can also improve traffic efficiency. Then also additional thing is that 40% of a driving actually in city is looking for a parking spot. So this also helps if we have autonomous vehicles which can drive by itself. Then they don't have to spend time for parking.
Zlatan, one moment, please.
Yes.
The slides are not changing in the video. Could you just perhaps check the presenting mode?
Yes. So they didn't change at all so far, or
No. We can see the PowerPoint app and just the first slide.
okay. Then I will change to. I will share my screen. It's better, I think.
Yes.
You should tell me this. I will share entire screen, and this should be
We can see slide 5 now. Okay.
okay.
Okay,
I will
it's
just
working now.
Yeah. So you can see the pictures which you missed. Okay. So we come to increase traffic efficiency. So the next thing is reduced emission. This fact is a bit combined with increased traffic efficiency because if we have a better traffic efficiency, we already have reduced emissions, but also additionally, vehicle can reduce fuel consumption because it has more information about the vehicle and it can operate vehicle on the better conditions. So for example, trying to reach operating modes which are more favorable regarding emissions. I will also show you something like this in the further slides. The next thing is giving mobility to handicapped. So this is actually also a big benefit because the autonomous vehicle can provide people who cannot actually use current days vehicles by themselves. And the final one is business disruption and innovation. So also autonomous vehicles actually open fields to new innovations and also new business models. So you see, for example, Uber or many different companies which try to get into autonomous vehicles field to have some robot taxis and to provide some new business models. So how does autonomous vehicle work? So first we have some environment, roads, infrastructure and so on where vehicle is driving. Then we have a vehicle which is operating and a driver. The vehicle, we perceive this environment using some sensors. So this might be LiDAR, radar and so on, ultrasonic sensors and many others. We can have some map data and also communication. So V2X, so-called communication vehicle to other devices. Then sensor measurements come to a perception. So perception interprets the sensor readings. So sensor provides raw readings, but perception provides meaning for this reading. So for example, from a raw measurement of some LiDAR or some radar measurements, perception detects, okay, this is pedestrian, this is object, this is vehicle, and so on. And also it uses multiple different sensors to get some meaningful data. Perceived data and perceived environment comes to planning layer. In planning layer, vehicle or the planner decides what is the best action to do in this kind of environment. So we have some situation assessment, we perceive what's happening around the vehicle, we also predict what other people will do in the traffic. So if we see other car approaching, will it turn right? So we can decide what is the favorable action for us to do. When we have some plan and we know what to do, this goes to a control. So the control actually is responsible for executing this plan properly. And these controls, such as steering and braking and acceleration, goes back to vehicle, and this is a loop which constantly goes in the vehicle. So for my work, what I present you here is focused on this planning part. So I will present you some work related to planning in different use cases. So just to mention that this work is done through ITeam project, and these are many partners actually which cooperate with us. Some also are associate partners which are not mentioned here, like University of Sarajevo. So we come to the topic then, the problem statement, the superhuman autonomous vehicle. So what do we mean by superhuman autonomous vehicle? So we define superhuman autonomous vehicle as a vehicle which has a better driving performance than human drivers in terms of safety, efficiency, and comfort. It is autonomous, so it means that it operates independently in all conditions human driver can operate. And for different use cases, such as we mentioned before, we have a different problem-specific vehicle dynamics, which is relevant for this problem, environment, and performance measure. So, for example, if we consider use case of highly performant vehicle like autonomous racing, then for sure we need more information about vehicle dynamics, because we are pushing vehicle to its limit, right? But also if we drive in very dynamic environment in some urban setting where we have a lot of other participants, traffic around us, then we have a different environment setting and so on. And in some situations, for example, we have a different performance measure. So in a race setting, for example, we want to minimize time which is necessary to make a full lap, but in other cases we might look for some other solution. As I said earlier, the focus of all of this is on the vehicle intelligence. So this means the decision making and control which we get using planning and control methods. So contributions of my work I will skip them. So these are more scientific, which are related what is exactly contribution to the state of the art. But in general, I developed more motion planning algorithm which can scale well and drive in many different driving situations. And also what we did was very successful. We solved several challenging autonomous vehicle use cases, and we demonstrated, for example, quite challenging multi-lane traffic driving with traffic lights. So how to drive in such very dense traffic situations. Also minimum lap time for the slippery road, also considering drifting. So autonomous vehicles, as we said, are our ultimate goal. So we want to come to the state that we have a superhuman autonomous vehicle, but this is quite challenging work, and it is not so. It's impossible to do it at once. So how we approach it? We approach it with different use cases. So one use case is energy efficient driving, where we focus to get the best energy efficient driving, to achieve the best driving from point A to point B using the least energy. The other use case is automated driving in some urban setting with urban highway. So we have multiple vehicles, multi-lane vehicle driving around, and also traffic light. And the third use case is performance autonomous driving. So this is a pushing vehicle to its limit. So we drive on some race track, and we want to achieve minimum time on this racetrack. So all of these use cases will use different methods, so learning, planning, and control methods. So first use cases we solve using planning and control methods, and this is energy efficient driving. So the task of energy efficient driving use case is to plan motion of a vehicle from point A to point B using the least energy, while complying to all constraints in simplest case, because we have also some things in other use cases. Here we only focus on speed limits, and also based on information which is available from net data. Challenges here are computational complexity. So it is quite challenging computationally to achieve this. Then we have some nonlinear models here, which are problematic. Then a long planning horizon. So this comes also together with computational complexity, because we have to plan for example, 20 kilometers in advance. And combinatorial aspects are problematic because some methods actually don't work on this problem. So these are formulas which I mentioned you, but you don't have to take care much about this. This is just to show you how actually what is in the background. So this is more or less, if you had a high school physics, this is a vehicle is on a slope, and we have some different forces acting on a vehicle, and we need to model these forces to then compute and to being able to predict how much energy which will vehicle use as operated on some for example vehicle trajectory. So to get the best driving performance, we need to predict how vehicle will drive for different driving trajectories. What we model here is air drag. So this is resistance of air, vehicle moving through air. Then we have a rolling resistance, so this is just a frictions. And then a third one is gravity resistance. So this is more or less resistance by gravity if vehicle is driving uphill or downhill. And then we model a motor. So we model a motor as a static map, and then we compute the full energy used for driving some trajectory. So what determines actually driving? Driving determines the velocity, more or less, because here we consider longitudinal velocity over the road. How we can present this? We can present this as a graph. So we have based on the distance. So the lower axis is a distance. So distance from point A to point B, and vertical axis is velocity. So we want to plan vehicle velocity which minimizes energy consumption. And then I develop some algorithms which go through this graph and then find the best way to do it. I will skip this part here just to inform you. We have a specific algorithms which need some kind of information and estimates how much energy vehicle consumes to being able to better compute this part. So the total energy consumption is sum of energy used for acceleration, energy used for fighting road slope, so going uphill and downhill, for friction resistance, and also for air drag and auxiliary. Auxiliary is very important because this is kind of constant load, so this might be also, for example, operational cost. So if you have a driver which is paid by hour, then you can put his wage into this formula and get some measure of how much it affects. So we have two conflicting here works. So if you look again on the distance and velocity based on the initial and final state, based on different velocity trajectories. So each one of these is different driving behavior. You see here that vehicle starts with some initial velocity from VI, and then it stops after some time on distance SF. Based on different driving trajectories, we have a different energy consumption. So we need to predict this energy consumption. And then when we look on this formula, this part of the cost, we actually see that one part of this proportion, so this is air drag force, so air resistance, this is proportional to velocity square. So this is very important, and I want to take you actually as a message from here as a regular driver. The faster you drive, actually the air resistance is not linear, so it is quadratic. And if you drive, for example, 20% faster on a highway, you consume more or less, this is just estimate, but you consume 40% more fuel. So because this is quadratic. And on the other side, so by taking only this, more or less the slower we drive, the less energy we lose fighting air resistance. But on the other side, we have this auxiliary which is proportional to velocity. So this means that the slower we drive, our travel time is bigger, right? So if we have a driver which we pay by hour, then slower we drive. Of course, if you are in taxi and it's slowly moving, you will pay more if it's paid by hour. So we can actually find some really nice sweet spot here, which is balanced between these two, and I provided also formula for this. And then we can use this to compute in the algorithms, and we can compute optimal velocity trajectory for some different roads. Here you see there is some road, so this is a distance. So going from 2 kilometers to 3 kilometers, we have some hill and then downhill here, and we find that optimal driving is to slow down a little bit before top hill and then speed up using gravity to accelerate after the hill. So I developed different algorithms to deal with this, but I will just speed it up because this is not so interesting. But happens is actually that, as famous experimentalist Mike Tyson said, everyone has a plan until they get punched in the mouth. So if we have some plan, we want know what is optimal velocity to drive, but there is a vehicle in front of us, and what should we do? We actually then come to automated driving use case, because this is how to deal with dynamic environment, and then we have multiple vehicles around us. So if we have a situation like this, so this is the yellow vehicle is our autonomous vehicle, and the purple vehicle is some other vehicle, and there is a traffic light in front of us. This driving situation we can represent like this. So we can take one axis along the road, and the other axis as a lateral axis for lanes. And then we extend this also with additional axis, which represents time. So we have this 3D space, which changes our dynamic problem into static problem. So for example, traffic light, which has some initial state, so it can be green, yellow, or red, it's now static, and then it represents some obstacle like this. So it is active, so we have yellow and red light after some time. Then the vehicle which is moving in front of us represents some region of this space, which is shown here. And then our goal is actually to find trajectory of a vehicle which doesn't collide with this region. And then algorithm works like this. You see here that vehicle try to go behind this vehicle in the same lane behind this vehicle, but there is no room. It cannot pass through this region because the vehicle in front of us is the last one catching the green light, and then after that vehicle it goes yellow and red. So vehicle has to stop. So vehicle algorithm looks for alternatives, and this is everything done automatically by algorithm. So it looks for alternative and finds that it's possible to overtake vehicle, change lane, and then pass beside this vehicle. So how we do this? We do using a search-based algorithm where we iteratively look for the solution. So we iteratively build these transitions, and based on all the possibilities. So in each of these transitions, so between each of these points, we generate many different variants which are possible using the vehicle model. So we have a different variant for longitudinal driving. So this would mean that from initial velocity, we can brake or accelerate with different grades. So you see here that this is the one which is maximum braking, and this one is maximum acceleration. Then we have a lateral motion variant. So it would mean that we stay in the lane and also we try to change a lane. And then with these combinations, we get a new possible trajectories. And then by building small parts of these trajectories in algorithms, we build a full trajectory for the vehicle. What is important and to show how this algorithm works, we build this full trajectory in for example, for 10 seconds. And then always we plan for 10 seconds in future, and then we know more or less we are prepared for the evolving situation. So we developed then this algorithm, and then we went to test this vehicle. So our validation methodology was like this. So we have a traffic. So we took realistic traffic scenario, and then in parallel we developed more or less the automated driving in simulator, and also made some driving simulator studies. So we took a human driving performance in same scenario, and then we tested this on a real vehicle on a proving ground. So traffic modeling. So for the traffic situation, I took the scenario during my secondment in Sarajevo from on the street of Zmaja od Bosne, which includes 3 traffic lights and three lane road with average. You will see actually later how the traffic looks like. So what we did then, developed automated driving software. So this planning algorithm to deal with this traffic. So what you see here on the figure left, you see that the white vehicle is actually our autonomous vehicle, and other vehicles are around us. And autonomous vehicle plans what to do for the next horizon. So you see that the vehicle plans for some initial state to some horizon in future. And on the right side, you see the same situation, but only a projection of this 3D space. So this 3D space, which was augmented with time, as I explained you earlier, you see it on the right side. So for example, this red vehicle in front of us, it's here. And you see that region, as we said before, the same region is here. And you see that this red vehicle in front of us is the last one catching the green light, because this is the traffic light, and the traffic lights here, you see it turns yellow and red. So our vehicle has to plan that it changes lane here, and then passes this red vehicle together. You see here that the vehicles together pass through the traffic light, one by next to each other. What you see here also is that the autonomous vehicle actually needs to speed up to catch this vehicle. Why? Because it has to catch this gap to change a lane, because the vehicle cannot change lane somewhere here relatively to these other vehicles, because there are these vehicles next to each other. So the vehicle has to speed up to catch the gap here, and you see here that the vehicle then starts changing lane, and then once it's fully in the left lane, it can pass the red vehicle in front, because it's in the next lane. So now I will show you the same thing in animation, and you will see that how vehicle plans always a new trajectory for the horizon in future and adapts decision to the changing situation. So you see how the situation evolves. Vehicle speeds up and then catches this gap, then tries to change a lane, changes lane fully, and then passes this traffic light together with this red vehicle, and all other vehicles stay behind. Same thing happens here. The vehicle speeds up, changes the lane, and then passes the vehicle. So what is happening in the background? In background, as we said on the figure we have many branches which try to find actually the appropriate driving trajectory for the full horizon. So they try to find, they see, okay, they cannot, and they have to modify and so on. So this is same as I showed on the figure before. And we do this until we find some full trajectory, and then this always happens in background. So now this is pause driving, so that you see what's happening behind. So we also tested this in more or less in a vehicle simulator, which has more dynamics. So parallel to this, now we come to, so parallel to automated driving development, we have driving simulator study. But the goal of this is, if you didn't see, actually just to introduce you driving simulator is device which is imitation more or less the fully realistically looking vehicle, so the full cockpit of a vehicle, and also it has a big screen around to provide full immersive environment. So you have a screen which is a circular screen around with 180 degrees field of view, and then you really feel what's happening. You have side mirrors which are screens and so on, and then we can get realistic driving behavior from a human drivers in a reproducible manner. So we were able to reproduce many different, the same scenario which we had for automated vehicle, we reproduce it for many different drivers, and then we see how drivers behave in this same scenario. So this is how it works in practice. You see here the vehicle, the participant is driving, and it's very realistic. Actually, it's in the screen, and there's a traffic light, and the participant more or less passed through yellow light. And then we did this study for 30 different participants. We collected more than 100 different driving trajectories, and on the same graph as before, you see here that this is a time and this is a distance, and these are full 3 traffic lights. So this is kind of zoomed out what you saw for algorithm. We see that these traffic lights are red lines, and then again green light, and then again red light, and so on, and this repeats. We can see that all different drivers, they have a different trajectories. For example, these trajectories here, you see here each of these lines is one driving trajectory. So this was one human participant drive for this stretch of 3 traffic lights. What happens here is you see that, for example, this participant, someone drive, stopped on the first traffic light, waited there until the traffic light went green, and then passed away. These are people who catch the second traffic light, so they had to stop on second traffic light. These are on third, and so on. And here you see lateral driving, so people made many lane changes, and there is no clear pattern actually here because people were changing on different positions. And this is also graph with velocity. So for example, you see here people, this is same axis as this longitudinal s-axis. So you see here many people stop on the first traffic light, many on the second, and many on the third. But what's interesting also, you see many people drive more than 60 km per hour, which was the speed limit. So the result actually showed this. So we had 69% people passing through yellow light, which was very interesting. We had 2 collisions, so 3.64% of people made collision because it was very challenging scenario. So the vehicle in front brakes because of the yellow light and so on, and so there were also some collisions. And what is interesting also that 50% of people break the speed limit, and also some even with 10 km per hour. What we showed is that automated vehicle is about 60% better than the average human driver, and also 22% better than the best human driver in terms of energy efficiency. So we took these automated driving trajectories and human-driven trajectories and then tested on a real vehicle. So in a cooperation with Volvo Cars, we tested this in Sweden. So this was an empty empty proving ground. So this is dedicated test facility where many of the driving features are tested and vehicles are put to the limits, and vehicle dynamics is tested, active safety systems are tested, and so on. And we had a Volvo S90 equipped with steering robot, which was executing this human driven and also automated driven trajectories. And then we tested them, and you see here that the vehicle was tested on empty ground, but the other vehicles are simulated. And you see here that we used only 3 left lanes, and you see here this is a real vehicle and it's passing through yellow light. So this is one of the human driver trajectories where vehicle passed through yellow light. The other human driving trajectory is quite aggressive. So this is a human driver which stopped on the traffic light. So you see here that the traffic light turned and vehicle fully stopped. And this was quite challenging stopping because it was like more than 12 meters per second square. And this was automated driving because vehicle, the same driving situation, vehicle knew in advance when traffic lights are changing and so on, and then it adapted its driving so that it can catch the green light. Then we took different passengers, and then we placed them to be passengers in these 3 cases. And then we let them to judge how they feel in each of these driving situations based on comfort and safety, and more or less they gave better grades to automated driving system than other human driving trajectories. And then we come to the last use cases. So last use case is performance autonomous driving. So this is more or less how to drive on a slippery road which has a low grade. So for example, imagine dirt road or snowy road or something like this, where you really have to drift into curves to keep high velocity because the wheel forces are not so high, and we can get some maximum wheel forces by having a larger slip angle. What we developed here is this algorithm for motion planning of this kind of driving using the same algorithms as in before use case. So just to not go too much into details, instead of motion primitives as we show later with accelerating, braking, and lateral driving, where we generate these motion variants as we explained, now we have a different models which we use. So we use one kind of model to have a kind of driving in a low curvature driving, so where it's like driving close to straight, let's say, driving, so with slight turns and so on. And we use this different second model which pushes vehicle to the high side slip angle. So this means that we are drifting. So if many of you know probably you saw some videos of drifting. So we use the other model which actually keeps vehicle in drifting. And then we combine these two models. We plan future driving by combining in heuristic search manner. So using a heuristic search algorithm, we combine these two, we remove which are going off a road, and then we generate motion primitives until we find some velocity, so some vehicle trajectory which keeps vehicle on the road. You see here that this vehicle trajectory keeps vehicle on the road. What is interesting here on this it seems that vehicle will lose control later, but actually in the next step this will be corrected. So this planning for a horizon enables us that we correct this over the time as we can. So you see this how it works in practice. So we plan for some horizon in advance. You see that there is a very tight curve here, and vehicle goes really to a slip, so the drift state, and then we drift to other side and so on. And same as before, what happens in background, so we plan many different motion primitives behind to generate these trajectories. As a conclusion, I'm giving you the general conclusion. So we had these three different use cases. So three different use cases which are solved with motion planning algorithms based on search algorithms. And then more or less this shows that we can achieve superhuman driving performance in terms of safety, efficiency, and comfort. We had some problems with computational performance, so it is working close to real time, but of course computational performance is big. I would just make some relations to this. So we are solving quite challenging problem computationally. So we have some possibilities to do. We don't, as a human, we don't consider this on everyday life, but we had possibilities more than there is a star in the universe. So this is similar to actually what is, for example, if you know AlphaGo is doing from a deep mind. We had on each stage of the problem around 100 different possibilities. And if we have a multiple stage, so if we plan for maybe 10 steps in future, we have a combinatorial explosion which is enormous. So to conclude, we managed to get some close to real-time performance, and we plan to future improve this. We also plan to improve some functionality, so we plan to consider uncertainties in the environment and vehicle model, and also interactions with other participants, but also to include limits of perception system. So if we have, for example, blind spot from our sensors and so on, and then following up on execution so that we know that the plans which we gave, that they are really properly executed. And with this, I would conclude my talk, and I'm open for the questions.
Thank you, Zlatan. We have two questions so far. The first one is, considering Tesla has the capabilities for autonomous driving 3+, but it is hindered by regulations, when will fully automated cars be allowed on roads?
Yeah, so this is a very good question. And the claim actually 3+ comes from Tesla. So we are not sure do they really have this. So the thing is that regulations are coming actually, and 3+ autonomous driving is possible. So for example, Waymo is more or less already providing some fully autonomous vehicles as a taxi service. So you can get into the vehicle where there is no driver. But the thing is that this actually works on some domains. So for example, on some region which is well covered by, and all use cases, let's say, which is well covered. What Tesla has is a bit different approach. So Tesla is commercial car producer, and they want to actually achieve this for regular drivers. So for the drivers which own the Tesla. So but everyone is agreeing actually that the problem of fully autonomous driving is not easy as it was expected before. So people made many different claims about the future and so on, but what is now clear is that probably something like autonomous robot taxis, or maybe autonomous trucks driving on a highway are more favorable that they will come. Because for many of these, for example, Waymo, you need quite expensive sensors to get the level of confidence that you can claim that you have a level 3. As far as I know, Tesla, although they are doing a very good job, they rely on cameras, which are sensors, which are, we as a human also have eyes, right? We use visual sensors, but we need also additional sensors to have a more robustness, and also to have more or less more guarantees to have this driving. And with these new sensors comes also additional cost, which is not so easy to put into every car. It is okay financially to put it into some robot taxi, and which will be used 95% of the time, but to have and to put some extremely expensive sensor which maybe costs as much as your vehicle, and to use it 5% of the time, then it's not well it's not good investment.
Thank you, and we have one
I
more
hope
question.
you're satisfied with the answer. I cannot give you something more concrete.
Thank you. So we have one more question, which is related to the previous one. How do we do verification and validation of such vehicles?
This is extremely good question. So one of the biggest challenges actually to having autonomous vehicles is actually the validation and verification of this vehicle. But I showed you in my case more or less was only one use case. So I tried validation in my case is met by having a superhuman driving performance in one use case. So this is very restricted, and maybe in some other use case it will not work nearly as good, for example, as human. Of course, we try to push it, and research is such that we push one frontier by another, right? And we want to get better performance overall. Uh, there are many works which are done on the verification and validation. One is, for example, to have a some scenario catalog so that you have a representative scenario. What Tesla is doing, for example, is very interesting. They have the full fleet of vehicles, so they can deploy in parallel some of the features and then look how they behave compared to other vehicles. So they are not active, but they work in background to a currently running system, and then they see and they note where are discrepancies to other, for example, how human reacted in some situation and so on. So there are many work, and also it's very live field. This so there are many things are based on this divide and conquer approach, that you validate sensors, you validate algorithms separately, and so on. So it is an extremely complex system, and it's quite challenging actually to do.
Thank you. We got another question. This time it is, do okay, so I will read into her comment first. First of all, I want to say big thanks to Zlatan one more time for mentoring at the beginning of my career, says Ahmet Muratovic. My question is,
Hello, Anna.
do you run real world testing, or are you just testing in simulator?
So I showed you actually one part of the real world testing. So this was in Sweden with on the test track where we ran our more or less uh, solution. But real world testing in Europe is quite problematic actually compared to because in Europe we still have these legal problems how to test the real vehicle. In Graz, what we have is also called Alplab. So Alplab is region of testing region close to Austria, and then it's covered also by some sensors. So we have parts of the highway stretch which are covered by sensors and so on. So it is possible to test some of these. And we have in virtual vehicle we have I think now three fully so automated vehicles with advanced sensors and fully drive-by-wire and so on. We also participate actually in RoboRace competition, which is autonomous vehicles racing. So this is newly established RoboRace competition.
And we have another question from Ahmed, connected to the topic. Do you test real world scenarios in simulator?
Can you repeat the question? Sorry.
Do you test real world scenarios in simulator?
Okay, I know why Amr is asking this question because his company is more or less digitalizing the real world and doing it in simulator. What I showed in my work is actually more or less realistic world, but manually mapped and manually arranged the same scenario from a real world. Uh, what is actually very popular is to have the virtual twin, so called, so that you really have a exactly same environment as 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 in real life in simulation. So we have also some work in this aspect, and we are developing. But maybe we can program and to establish some collaboration.
I could give another minute maybe if anyone else has any questions, and if not, we could finalize the topic. Is that okay with you, Zlatana?
Yes, sure.
Okay.
Maybe just as a final conclusion, I would try to promote this autonomous vehicle driving field for all of you. This is not only autonomous vehicles, so in general, this is more or less field of robotics, which I think we are on some edge of disruption into this new field where things will be autonomous and we will have many different shapes and many different forms of these truly autonomous intelligent systems around us. And I think it's very interesting field to be for some young engineers wanted to make some impact in your career. And what many actually compare it's like the autonomous vehicle. They compare it to a Mars mission, so that it's more or less as hard as Mars mission.
I completely agree. It seems we don't have any more questions, so I would like to ask you if I could be allowed to share either your LinkedIn or your email for anyone that might have questions for you in terms of the career or the presentation later on.
Of course.
Okay. So thank you once again from the BH Futures Foundation for taking the time to be here and to talk about this topic. It was a very interesting presentation, and the answers for the QA segment were very in-depth and very informative. So thank you very much.
Thank you very much, and I'm glad that you enjoyed.
Have a nice evening.
Bye.
Bye.